Welcome everybody to today's Friday seminar. We will have a split presentation, first by Adam Rifaie, then by Jaroslav Nikityenko about exoplanets. I don't know how much there is about discovering and how much about naming that we will learn during the talk. And I first give the stage to Adam, so please start your presentation.
Hello, can you guys hear me? Okay, perfect. My name is Adam, as introduced. Jaroslav and I will give a brief introduction onto exoplanets and a little bit on a specific exoplanet known as GJ486b. This will all correlate to what we are trying to talk to at the end of the discussion, which is proposing a name for the Name ExoWorld 2022 project, which I will touch up on later in this presentation. So, exoplanets, as the name kind of indicates already, they are essentially planets that are outside of our solar system, as in there's a clear definition as to how planets are classified, and the typical idea or general idea of how exoplanets came to be are similar to how we assume the planets in our solar system also came to be. This is via the solar nebula theory. It's a theory that hypothesizes how a gas cloud condenses down into a star, and while this is happening, planets are being created at the same time. It kind of gives an explanation as to how gas giants such as Jupiter, Saturn are further away from the star, and colder, or technically rockier planets are closer to the center, like Venus, Earth, Mars, so on and so forth. A couple of examples of exoplanets that are quite interesting, at least I found it to be. One of them is the WASP-12b. It has this very iconic shape, mainly because it is a Jupiter-like planet, which is essentially a gas giant, but it is too close to its own sun that the sun starts to accrete matter from it. So it has this weird egg-like shape. The solar nebula theory suggests that the planet shouldn't have been created in the position that it's in. So people assume either a catastrophic event or some kind of friction moved it from outside of its solar or outside of its star system closer to its center. Another example, very well known, is the TRAPPIST-1 system. It essentially has 7 rock-like planets similar to our Earth, 4 of which are potential replacement planets for our Earth, if we can call it that. A very iconic picture from the NASA poster collection is an image of how one would see the other planets from the TRAPPIST-1e planet, which can be seen here. The next system that I wanted to describe is known as the Kepler-16b system. It essentially is a circumbinary system, i.e. the planet revolves around around a binary star system, which is very iconic in several situations, as in, for example, it is also similar to the planet Tatooine in the Star Wars universe, for all the Star Wars buffs out there. And one iconic thing would be that you would always have a companion shadow. You would never have a single lonely shadow. So the typical detection methods of how exoplanets are detected are numerous in number, but I would focus on a couple of them here in this talk. The first one being the Doppler method, as seen by this animation. Due to the mass or the star system essentially revolves around a center of mass, although when the star's mass is relatively large, it's hard to notice this, but every star system has this concept. So if you look at the bottom left side of the image, that is roughly a visualization of what one would see if one were to observe it from Earth. as the star approaches closer towards us or towards the Earth, say that we are somewhere in the south side of this image, due to the Doppler shift of the photons as it's approaching closer to us, the spectral lines would be blue shifted, and as it's moving further away from us, the spectral lines would be red shifted. This was the earliest method of how exoplanets were first discovered, although it is a more complicated method than what is about to follow. The second method, also known as the transit method, is far more intuitive. It essentially measures the brightness from a relatively constant star. And as the planet transits or eclipses the star, one would see a sudden drop in the brightness, as shown in this short animation on the top right. Clearly this method has its own issues, like the Earth has to be aligned with the plane of the star system, and it's hard to detect, but due to the sheer number of stars, this is one of the most popular methods in which over 3,000 exoplanets were discovered via this method. And finally, not as popular currently method known as astrometry. It uses the same principle of the center of mass as mentioned for the Doppler shift, but the star is observed clearly in the visual spectrum to be moving. This is very hard to detect, typically because the stars are much larger than their planets. But with high-resolution cameras, one would be able to do it. And speaking of high-resolution cameras, we will go into the different types of instruments that are used to detect these exoplanets. The first one I want to highlight is the Kepler satellite, which uses the transit method. One of the most famous ones ran from 2009 up until 2013 and has documented well over 3,000 images via the transit method. The second one I want to highlight was the Gaia. It was recently released, recently 2013-ish, and it uses the astrometry method with a resolution of down to 20 microarc seconds, which is at the peak of resolution when it comes to taking images of exoplanets. And finally, a recent image from the James Webb Space Telescope, which shows which kind of glorifies how powerful the camera is. And you can see at the center the planet that it was taken, again, infrared image, because the James Webb Space Telescope primarily works in the only works in the infrared region. Lastly, I want to touch up a little bit on the planet that we are going to be talking about here today, which is the GJ486b. It revolves around the star GJ486. It's a rocky Earth-like planet with a really high temperature. This is at the bottom right, one can see like an artist representation of what the surface might look like. And I'm not sure if you might have noticed, but typically planets or exoplanets are named after the host star. So GJ486b is the planet for GJ486. And this GJ486, for example, comes from the catalog that it's documented by, also based off of the instrument. So GJ here stands for Gies, Jahr, Reise. It's like the catalog that holds all of this information, which is a very methodical and calculated way of naming exoplanets, which is necessary for documentation. But when it comes to more down-to-earth kind of naming, the IAU has implemented this project, which is known as the New Exo Worlds 2022 project, which is a global outreach project. This project gives every country the opportunity to name one exoplanet and one star. So we are taking this opportunity, Yaroslav and I, to present or propose a name for this star and its star system. With that, I would like to thank you for your attention and your time. And I would hand over the stage to Yaroslav if there are no further questions. Thank you.